So, okay. Hey, welcome everyone. My name is Clint, and I'm going to be presenting this afternoon on Couchbase application clustering, or specifically writing a clustered application on top of Couchbase and some of the techniques you can do to basically remove some of the external dependencies of your application. So a little bit about me, just to introduce myself quickly. I'm a solutions architect in the office of the CTO for Cisco. I work in service provider video, so Cisco's the leading provider of video technology to video service providers around the world, and that's my primary role day to day. As a little bit of background and context of this. So Cisco, we've been working with Couchbase for several years. We've been shipping on Couchbase since 2012, actually pretty much right at the introduction of Couchbase when the marriage of MemSQL and, Memcached and CouchDB, and right at the point of that, we jumped on board and started using it for some of our applications. We're running mission-critical, very large-scale deployments on-premise and as a service all around the world. We've got data sets in the billions of records doing some pretty high transaction rates, and so some of this will be some lessons that we've learned on writing applications on top of that. So what I'm talking about today is creating an application that's clustered and glued together by Couchbase, and using then lightweight code snippets to replace some of the other services that we typically have in our head-end. So these are things like Zookeeper and Eureka and Console and RabbitMQ, HornetMQ, et cetera, et cetera, et cetera. And the purpose of this is basically as follows. A lot of times, apologize a little bit of the cheesy visual, but a lot of times our applications kind of start looking like this, where we have a little application that we're wanting to deploy, and we start pulling the dependencies, and you get this pretty rat's nest of dependencies that you're having to work through. And that's what we're working to untangle a bit in this hour. So what this looks like is, as you build applications, you typically start with your app instance and a load balancer, and then a backend database like Couchbase. And then you say, okay, I need a way to do queuing, and I need a way to do discovery, and I need a way to do all the other sorts of nice fun things that you need to do to make your application work internally as well as with other applications that are co-deployed alongside of it. And then you start deploying those technologies, and they start bringing along their own dependencies, and then those dependencies sometimes bring along those dependencies, and you end up in a pretty hairy situation. And what the tack that I took a couple of years back when developing in some of the application development I was doing is looking to cut the cord on that and to trim that down, and so that when we deployed, it was just simply a very bare bone minimalistic stack of app instances in Couchbase. And to run through some of the reasons why this is important, what's the value of this? First and foremost, it's just complexity kills. The second is machine count matters. In some environments, this is more sensitive than others, but when you're deploying a service and you then end up often doubling and tripling the deployment, the VM count for all the dependencies of the service, you double and triple the cost, whether it's in physical hardware running in your local data center, whether it's Amazon, Azure, whatever instance is running in the cloud. There's also organizational needs. I'm sure, at some point in your careers, a lot of us in this room have had the conversation of going to the operations team and saying, for this application that we want to deploy, we need this particular queuing technology. And they're just like, another stupid bleeping queue, and then you get into we have Hornet MQ, why are you using, Rabbit or whatever? And the reality is every dependency that you have, every dependency that you deploy really ups the operational complexity. It's another entity to monitor. It's another skill set that you have to staff for, and that can be. That starts to be a major tax and a major burden on organizations. Application needs. And this is something that's probably is not necessarily prevalent for everyone, but so I work for Cisco, and we're a company that ships software that deploys on sites, that goes on other people's networks and deploys there. And so when you have a simple application to deploy that could be deployed very quickly and has a very minimal footprint, customers love your application. When you sit down and sell them on your application and then start rattling off a list of 30 dependent services that you need to make your application run, they start thinking a little bit about whether they like the complexity of keeping your application up and running. There also is, in this approach, a little bit of a love of roll your own. My background, I spent several years as a C developer, and I think the ethos of writing your own libraries instead of spending the time to learn someone else's buggy libraries has kind of stayed with me a bit. And then the final reason is a very minimal feature set, and this is a big plus because there's less things that can go wrong. There's less, when the larger and larger scale that you get, the more that you are dependent on things being just very, very simple. Simple operation scale, simple architecture scale, and if you have very simple operations that you start with, they scale very well. If you get yourself hooked onto very complex feature sets, you often find yourself in the end in some very untenable situations as you scale your application out. So, and then some minuses. Why not? Why is this approach bad? There's more application code to maintain, and it's nice just to leverage someone else's code and not have to write your own. Schema changes are difficult, and this introduces some more areas where you're subject to schema changes. You may be if you're in an environment where you've got a very stable, mature platform stack that you can readily plug into, then there's no need and no benefit and no value to recreating your own. You may not have a sensitivity to deployment footprint. If another couple of VMs is not a big deal, or even another 10 or 20, then it doesn't matter. And then finally, it is also a minimal feature set. It's the approaches that I'm going to discuss today. They're very, very easy to get started, but to recreate the entirety of a Zookeeper or a console or whatever is years and years in works. It's hours to get started, but if you need the entire feature set, you probably want to leverage something out there. So now to run through, so now I'm going to just step through some of the common functionalities, some of the common application functionalities, and look at techniques and how you can replace them with just very simple, straightforward application logic on running against Couchbase. The global distributed lock. So this is commonly used to if you need to serialize functions that are running across the large clustered application, make sure that they're serialized, make sure that they're not running at multiple places concurrently and stomping on each other. Then you have to deploy a lock, and then because you're across multiple machines, it needs to be distributed. This is a functionality that you can find in Zookeeper, Console, and more. The basic flow for this on Couchbase is pretty simple. It's a handful of lines of code. You form your lock document. You do a get on the lock document. This is just your common LCB get with a lock and a timeout. And if someone else says it locked, you're going to get a failure message back, and you know, hey, it's busy, it's locked, and I need to either retry until I can get the lock or give up, whatever your sort of use case is. The code for this against Couchbase is, I referred to in this and to our wrapper functions just to have a little bit of a simpler thing, but it's just a handful of lines of code. Get your lock, or have a wrapper function that basically does a Couchbase object get with the lock key and a lock timeout. And if you get a valid return with the CAS value, you're good. And then when you release it, you just do a set using that CAS value again to release the lock. Leader election. So this is used to have a dynamically dedicated master that's for ongoing activity. So you'd use like a distributed lock if you just had something that was occasional, that would pop up every now and then. Leader election is you need to have an instance in the network constantly doing an activity, but you can only afford to have one doing it. And so this is maintenance processes. We use this a lot for doing like timeout processing. Again, another functionality provided by Console, Zookeeper. I'm hoping that people will be more pleased with this algorithm than with the result of the leader election algorithm last night. So again, this is relatively simple logic. Again, you just create, if you are the leader, you try to this works on the same concept of basically you're trying to conceptually get a token out of Couchbase and hold it. And so if you are the leader, if you're currently master on for a given key, then you refresh the document every few seconds, and you do that just by doing a replace on the key. If you're not the leader, then you try to create it every few seconds. And if you're able to create it, then that means you're the leader and no one else has the token. And that means you've won the election. If you're not able to create the document, you've lost the election, and you just return to your normal citizen ways. Again, code on this is pretty straightforward, pretty simple code. Elect master. If you have the CAS ID for the object, you do a replace on it to refresh it. Otherwise, you do a set to try to obtain it. If you succeed in that, then you are the master, and you're elected as the leader, and you proceed on. Discovery service. So discovery service. So this is used to discover endpoints for specific services in the cluster, and then also supports basic load balancing, health check, etc. Very common functionality and probably I think the most prevalent use of Console, Eureka, and DNS are also prevalent here. And this one is also just, again, pretty simple. You create the key. We have a document that's associated with the key that is a list of the nodes that are advertising themselves under that ID. And then their node IP address and the update timestamp for the node. And so every few seconds, each application instance pulls the document down, iterates through the document, kills out anything that's still in there, and this is how you handle nodes that have gone away, nodes that have died. It's by pruning out any of the stale entries, and then inserting themselves into the document, and then writing that back to Couchbase. On the discovery side, also just very simple logic. Your app instance says, I need to go talk to this application or this application. Pulls it out of Couchbase. It has a set of nodes, randomly selects one to get load balancing across the set, and then talks directly to that node. And so what sort of walks through. So all of your application instances advertised, in this case, we'll just say foo, and their instance IP address to Couchbase. Your other application service comes along, says, okay, I need to get foo, pulls the record for foo out of Couchbase, chooses an instance, sends a request and then sends the request directly to the selected instance. Shared queues. So shared queues. So this is I think a pretty common use of Couchbase already. So create a shared queue that's used across a set of nodes to queue up activity that's coming in that you need to handle across your set of nodes. So adding to queue, very simple. Just form the queue document name and append. One trick that we do that helps really scale out the queue is the actual, if there's details about what needs to be done, we store that in another document, and the only thing that's actually put in the queue is the document key, is the key for that document holding the details. So then when you're reading off, you're gonna go get the queue document, and that's gonna be a get with a lock, because you need to block temporarily while you have it, you need to block people appending to it so you avoid the race conditions. Pull off a chunk of items and remove that from the queue, write it back, and then if those documents are document IDs that you then need to pull to get details, then you pull each of them and start working on them. And then transactions. This is another technique that we use Couchbase very heavily for, is as a globally shared transaction system with rollback. So to show kind of a common usage for this, you've got an incoming request to an application instance, and then in order to process that, you need to call another service. You need to make a service request to another tier, and you do the common design pattern of giving a callback URL, so you don't have to hold open the connection while it's processing. The other application does a callback and ends up at this point on a you don't actually know what instance that's going to go to. You call another, you call it somewhere else in your network. You do another service request with a callback URL, and this time the callback fails for whatever reason. That node goes down, whatever, and you lose it. And this is where transactions go in, is because often depending on your application use case, for a lot of the stuff we do a lot of stuff that's very stateful. We are setting up policy sessions, bandwidth reservations on networking equipment, and various things like that, that if your overall operation fails, there needs to be cleanup. So any time where when you have like a mid-transaction failure, you have a cleanup. This is a very effective technique. So the basic approach is create the transaction, and the approach that we do is we take two records. So there's a transaction state record that's just a very simple JSON document that just has state of active and time equals current time, and then a transaction log. As we're executing the activity and going through sort of each step of the activity, call node 1, call node 2, do step A, do step B, C, D, E, F, whatever, you update the transaction state record with the current time, and then you append your activity, each step of your activity to the transaction log record. If you reach a scenario where the transaction failed or timeout, and if it failed, you have to know on basically in memory and on the node that you're handling. There's other scenarios in which you're doing a query to discover that it timed out. You're doing a maintenance job to discover everything that timed out. Then you pull the transaction log, iterate through the transaction logs in reverse, and undo each activity. And then close out the transaction, whether it's successful or whether you had to roll back by just simply deleting the two records that you created. So, thank you. That's all I have. Any questions? No. Yeah.
What is the throughput or the TPS with this system have been deployed?
So, yes. So the question was, what's the throughput of the system? So we hit high hundreds of thousands of transactions a second against Couchbase. Interesting thing, is there's a lot of these principles that that violate, I guess I'd say, old school database design, where there's always been the old school idea like never use your database for IPC. And this is exactly what we're doing here. We're using the database for IPC, and it takes that and stomps all over it. The reality is it's like the amount of traffic that this generates on Couchbase, it's just a few percentage points of load at most. And it's minimal compared to the overall, everything else we're using Couchbase for as a database. So it's very, very minimal impact to Couchbase itself. In terms of some of the performance characteristics, these techniques, I mean, the distributing queuing, we haven't actually benchmarked it to max to failure, but I mean, in production, we'll regularly see it getting upwards of 10,000, 15,000 queue adds a second, with active polling across lots of workers, and no problem, no impact at all. So it's a very, very robust technique.
How many cloud-based nodes?
6 to 12. Depending on the point, yes.
So with your transaction system, if I understand correctly, you're saying that you use a separate Couchbase cluster as Scratchbase and then move it into the main thing?
Not cluster, just separate records. So we do two records. So one of the techniques that we do a number of things to sort of like namespace or documents to make sure that when you do searches, when you do MapReduce queries, or nickel queries and whatever, that you can be very specific about what you're asking for without having to, and tolerating, I guess, a greater degree of flexibility for application developers, because I think one of the problems you can have on something like Couchbase is that it's easy for an application developer to introduce a variable that then put a key in one of their documents that happens to collide with one of your queries. So we very, very heavily use a lot of namespacing techniques. One of the things that we often do is we only write things in JSON that we only when we very specifically want to be able to query them, either through a MapReduce or NoSQL. If our use for the document is simply as a document to get or put, then we will write it in XML, just simply so it's not JSON, and so it's not. There's no chance of it getting indexed and picked up in any fashion. And then the other benefit of that is when you're doing things like queues, or logs, then those we actually just treat basically as ASCII, and you can use the append function so you can just send the details over. So rather than, if you're doing like an XML or a JSON, you have to pull the document back, insert, write it back, which, I mean, Couchbase is blazing fast. I mean, it's a few hundred microseconds for that, but it's still, limits to, a couple of thousand of updates on a specific operation, on a specific document they can do. When you're doing the just pushing an update where that's applied server side by Couchbase, it's very, very scalable in how often you can iterate a document. There. Did that answer your question? Yeah. Any other question? So, okay, well, thank you. Enjoy the rest of your day and safe travels back.